and good evening, good morning, depending on where you are. And I want to first thanking to the organizer for inviting me and giving me the opportunity to give this talk. It's a wonderful workshop. I already learned quite a lot from the previous speaker. The host has, okay, it should be okay. Okay, so today I will talk about something which I have done recently with my colleague. So before I go into any more physics, let me first introduce my colleague, collaborator. So Akihiro Ishibashi-san, he is in the Kinki University in Japan. And also Kengo Maeda-san, he is in the Shibaura University. And they have done lots of work. So I'll talk about the work recently I've done with these two people. Okay. So the paper is following. Okay. So this is a first paper which I have written and put it on the archive on last November. And the second one, I have put it on the archive recently in the last August. Okay. So anyway, so let me start with my title. So my title is, I'm just giving some joke. So the title is ANEC. No, it's KNEC. So the crucial point is this she. And we're going to claim that this she is very important throughout my talk. Okay, so that's the main message I want to deliver. Good. So let me start with references. So I already mentioned that I have written two papers recently with these two gentlemen. Okay, the first one is basically about odd dimension for the boundary field theory. Namely, boundary field theory is 2 + 1 dimension, for example, or 4 + 1 dimension boundary field theory correspond to the first paper. And the second paper is boundary field theory is even dimensional. Say 3 + 1 dimension correspond to this example. Okay, I just listed up some of the very important and closely related work which influenced to my work, and that's this work. And what they have done and so on, I'm gonna introduce throughout my talks. And also I just want to comment on there's a nice paper by Gaon Waldo, which also I will explain throughout my talk. And just slightly mention what this have done, which is connected to our work. And that's references, related references. So let me start. So as you may guess from what I say already, D is even or odd dimensional boundary field theory. I will make a big assumption for my talk, throughout my talk. And the assumption is holography, ADCFT. Okay? Especially, I assume that given the boundary D-dimensional quantum field theory, okay? Here, D is even or odd, okay? Given boundary field theory, I assume the existence of the D + 1 dimensional bulk dual, which is written in terms of the Einstein gravity. And that is a big assumption, but throughout my talk, I assume this. And using the property of the ADCFT, we plan to discuss the physics through that. Okay, so that's my big assumption. Okay, good. So today's topic is the following. So my plan is following. I first give the introduction and motivation, okay, briefly. And then before we go into the technical detail, I just summarize my message, main message or main conclusion as intuitive as possible and in 2 pages, as simple as possible. And then to convince you how we reach this conclusion, I just give the simplest example to illustrate how we reach this conclusion, okay? This is the simplest example which I will deliver in today's talk. But in the paper, we worked out more complicated and more generic situation. But since this is an online talk, I thought that it is better to give the simplest example to illustrate how this works. Okay, so I only in this talk give the simplest example. But the result is quite generic. So in the end, we discuss how generic the result is and how in simple case, it's going to be like this, but in complicated situation, how this is modified into this, discussion and open question. And that's a plan of today's talk. Okay. Let's see. Good. So let's start with the introduction and motivation. So the first part is very, well, slow and dull for some of the experts, but let me start with a simple situation. So we assume that AD is shifty, okay? So that means given the boundary field theory, which live in the, say, sphere in this example, suppose that's three-dimensional space-time, okay, 2+1 dimension. So the boundary is a sphere and time. I assume that there's a holographic bulk there, meaning that the four-dimensional bulk, which is described by the Einstein gravity, okay? And all of the AD shifty, so-called the dictionary, I assume in this talk, okay? So let me start with a very well-known fact about AD shifty. So in AD shifty, the GKPW prescription tells that how can we calculate the two-point function or correlator of the boundary field theory in terms of the bulk. Okay, that's the first evidence of how the holography explicitly works. So how does this work? Let me give the simplest situation. So suppose we inserted some operator, okay, in here. By the way, everybody can see this yellow one?
Yeah,
good. So suppose I inserted some operator, okay, in here. Now, suppose I want to consider the two-point function. Because I inserted operator in here, let's say other operator is inserted here, okay? So we have two descriptions of how these two operator is correlated, which gives a correlator or two-point function. One, okay, let me use a different color. One, we inserted operator in here, and that effect spread through the boundary, okay, and reach here, okay? So suppose we want to consider the, say, Green function. We inserted operator here, and that effect propagate through the boundary and appear here, and it appear as a Green function, okay? Insert operator, and then we obtain the causal result. So that's one description from the boundary viewpoint. The other description is, of course, through the bulk, okay? We inserted some operator in the boundary. Now we have the AD safety dictionary, okay? Giving the operator in here, we excite some bulk mode, okay? And that bulk mode propagate through the bulk instead of through the boundary, and then come back to this boundary again. So that's a bulk propagation, okay? Now, as everybody knows it, AD safety tells that these two calculation of the two-point function coincides, okay? No doubt about that. So let me ask, given that, following question. The spread of the effect of the operator inserted here in one description propagate through the boundary, but on the other description propagate through the bulk, okay? They are equal, right? But suppose we focus on the boundary only, okay? The effect of the insertion of the operator in here now propagate into this point here, but that propagation is at most causally the same as velocity of the light, or always slower, okay? Suppose we are given the boundary sphere, this point and this point, and we consider, say, timeline curve, okay? If this is a 2-point, how fast can the information of the insertion of the operator in here can propagate into here, okay? The maximum velocity is the velocity of the light, which is determined by the geometry only, okay? The real physical propagation of the information of the effect of the operator can be equal to the velocity of the light, or causally it's slower, okay? So that's boundary causality. But as I mentioned, AD safety gives the two equivalent description of the two-point function. One is boundary, and the other is through the bulk. But I mentioned that they give the same result. So this propagation or this propagation gives the same result. But note that because this boundary propagation is at most the velocity of the light, or slower generically, okay? Suppose we have boundary field theory where you have many particles, and furthermore assume we have the quasi-particle picture hole. Well, in generic, boundary field theory, which is strongly coupled, we don't expect quasi-particle picture to hold. But suppose, okay, the information tried to propagate from point A to B, but there's many particles which bother. So real propagation is slower than the velocity of the light. Okay, that's usually see. Okay, so real propagation of the operator from here to here is at most the velocity of the light causally, or usually slower. But since this time is the same as this time, we expect one conclusion that the real causal propagation from here to here, if you just look at the geometry only, okay, forget about the degrees of freedom. The boundary causal propagation from here to here is equal or faster compared with bulk propagation. Why is that? Bulk propagation is the same as boundary propagation. As I mentioned, boundary propagation is equal or slower than the boundary null line, okay, which gives the fastest one. So we reach that the bulk causality curve is always or at most equal compared with the boundary null direction. So is this intuitive explanation clear to everybody? Okay. So in my talk, actually this is a property which we can prove. And in fact, it's proved by Gao and Ward long time ago, which I already mentioned in the references. But let me put this point aside. In my talk, I assume that based on this intuitive understanding, that the following principle hold generically. This is my furthermore assumption. My assumption is the following. If you look at the 2 points in the boundary, okay, the fastest way to reach from point A, let me say this point is point A, and other boundary point is B. The fastest way to reach from point A to B is through the boundary. Okay. Why? Because if you go through the bulk, and that's the same as boundary operator's propagation, but that is always slower or at most equal to the velocity of the light between A to B. Okay. So the fastest way to reach from point A to B is along the boundary by the velocity of the light. If you go through the bulk, it always gets slower or at most tied to the boundary velocity of the light. Okay. So this is a expectation and which we take it as assumed principle. This principle, well, it's an assumption. We call it as a no bulk shortcut principle, meaning that the shortcut between 2 boundary points A to B is along the boundary. If you go into the bulk, it always gets delayed. Okay, that's a principle. No bulk shortcut, and that I will assume in this talk. The goal of my talk is that by assuming this no bulk shortcut, which we usually expect, okay, from the following logic, which I already explained, what is a non-trivial result we obtain for the boundary field theory? Okay, that is the main question I want to address in this talk. Okay, so before I go into the technical detail or more explanation, are there any question so far? I hope this explanation is clear. Okay. Okay, so let me go ahead. So here is my another example. Think of this plane as a boundary field theory. Okay, I just put 2 points in the boundary field theory, point P and point Q. Okay, these are the 2 points. And this screen you can think of as a boundary screen. Okay, and imagine that on the perpendicular to this screen you have the emergent bulk direction. You can imagine that. Okay, now I ask the same question. Given the P and Q, okay, what is the fastest way to reach from P and Q? Okay, you can see that this is a spatial direction and this is a time direction in the boundary. Okay, so I wrote it down already the null direction here and here. Okay, so if you start with a P, if you go by the velocity of the light, you are guaranteed to reach this point Q. Okay, and in addition, I consider both P and Q is achronal. Okay, let me mention a bit about achronal. Imagine that your boundary is sphere, like the surface on the Earth. Okay, you want to consider P as a north pole. Okay, I write it down here. So P is a north pole, and Q is a south pole. Okay, so depending on where you are, I ask the following question. Suppose you want to ask the shortest way to reach P instead of the Q somewhere else. Okay, let me do it in this way, like here. We are living in the north hemisphere. So suppose I want to reach this point. Okay, say suppose this is Japan or Korea. Okay. If this is a point, you may think that there is a two or more way to reach by the velocity of the light. Obviously, the fastest way to reach this point from Q is obviously along this way. Okay, if you go by the velocity of the light, from here to here, this is the fastest way. But even though you go by the velocity of the light, if you go by this long direction, okay, you reach here, but when you reach here, okay, this point, okay, even though it's connected by the velocity of the light, this is not the shortest way to reach from here to here. Obviously, this is not the shortest way. The shortest way is to reach here, okay? In order to avoid such a confusing issue, I consider North Pole or South Pole as my P and Q.
Excuse me, Nori.
Yes.
I mean, do P or Q denote spatial point or space-time point? Or the intermediate point X that you draw?
Okay, I'm abusing the language. So in this figure, P and Q is space-time point. Right, you are right, you are right. But here, I just write it down P as a, I use a different language. Here, P and Q is obviously space-time point, right? Here, I just put A and B. Okay, I ask how to reach A to B in the fastest way. In order to avoid G's extra confusion, I consider A and B as a North Pole and South Pole. That's the only thing I want to say. Is it clear?
Okay, okay.
If A and B are North Pole and South Pole, then what is the time to go from A to B by the velocity of the light? It's uniquely determined, right? So that's all I mean. Okay, sorry for confusion. Oh, hope, is this okay?
Yeah, thank you.
Okay. So here it's P and Q is space-time point. Sorry for that. Okay, so here it's like rho equals 0 is my A. So rho is my south pole, and rho is pi is my north pole. Okay, so I want to go from south pole to north pole. Okay, in order to avoid this confusion, I consider P and Q are north pole and south pole, and that is more to say that A and B I want to consider as achronal to point. Okay, that's the situation I want to consider. So I want to consider rho to pi, 0 to pi, south pole to north pole. Okay, now if this is a velocity of the light, if at the time of this v is v naught, which is determined by the velocity of the light, if you go into the bulk starting with this p, okay, starting with the south pole, this is a boundary screen. But instead, you consider the bulk causal trajectory. Okay, bulk causal trajectory starting from P on the boundary, but you go slightly into the bulk where G is non-zero. Now, come back again to the boundary point where G equals 0. Okay. Suppose you find the bulk causal path. Okay, which started with a P at G equals 0. G is a boundary emerging direction. G0 is a boundary point. Start with a G equals 0 at P, south pole. You go into the bulk and then come back to the boundary point. If you come back to the boundary point in here, suppose, okay, then you find faster route through the bulk. Why is that? Because if you find the bulk trajectory going to here, see, at this moment, when you reach rho equal pi, you are already taking the shorter time, right? But if you find the bulk trajectory and you search for the fastest way to reach to rho equal pi, okay, through the bulk, you end up the fastest way to reach rho equal pi through the bulk is say here. It's guaranteed that your bulk trajectory is always slower trajectory, slower causal curve compared with the boundary null line. Why is that? The fastest way through the bulk is here, okay? See, in here, let's see. So when you reach here, then it takes more time compared with the velocity of the light, right? So if you say, whatever bulk trajectory, you start with this point, okay? You go into the bulk, and then you come back to the boundary point again, okay? Boundary point around here. The fastest way to reach from here to here through the bulk is in this range. We say that bulk trajectory always gives a time delay compared to the boundary line, right? But if you find accidentally the smart trajectory through the bulk, which gives this path, okay, then you say that the bulk allows the shortcut compared to the boundary null line, right? So as I mentioned, reasonable situation allow me to assume that there is no bulk shortcut, okay? That means if we go through the bulk trajectory, we are guaranteed to reach only in this region, and this region we don't expect. That's a physical expectation, okay? So as I mentioned, I take this as an assumption or principle. I consider any bulk trajectory starting with this point, which goes through go into the bulk, and then come back to the boundary point. I ask, when we reach to this V equal V naught line, which is the same as this Q, okay? The bulk trajectory can allow the trajectory to reach into here or here. That is the question, okay? I require that any bulk trajectory can never reach into this region. That is my requirement, that there is no bulk shortcut, okay? My question is that by requiring that whatever bulk causal curve, which is causally allowed, we consider if we impose all bulk causal curve are not allowed to reach here. It's allowed only in this region, okay? What does this requirement gives in terms of the boundary field theory? That is the main question I want to ask, okay? So I hope, is this my question or my setup clear for everybody? Okay, good. So I just repeat what I say. What does this no bulk shortcut principle, which I assumed, okay, imply in the ADCFT? That is my requirement, okay? That is my question. So just to give the illustration, let me give the simplest example. The simplest example I consider is following. As I mentioned, I consider 2 + 1 dimensional boundary field theory as the simplest example. So the boundary is just 2 spheres, okay, and time. Well, this is the simplest example. So the boundary metric is the time and sphere. Okay. Hope this is as simple as possible. So just pardon me. Now I just massage this metric in this. Now nothing is weird at all. I just define t and theta in u and v, okay, to see the causal line. So in this definition, this become this, okay. Theta simply become u v, u minus v, okay. So that's my metric. The only one point is that since theta has a range and phi has a range because it's a 2 sphere, okay. As a result, theta and phi, or correspondingly u and v, has some range. Well, t has a infinite range, so u and v doesn't have the range, but I just explained. Theta and phi has a range. That's the only thing I want to say. So this is a boundary metric. Okay, hope this is as simple. Good. So I ask the same question here. Okay, so here instead of the row, I just put it as a theta equals 0 and theta equals pi. Such a thing I consider. Okay. Good. So here, as you can see, I take this v direction as my affine parameter. Okay. Why is that? Because in the boundary direction, b is obviously affine parameter. Okay, to reach from here to here. So I take the u equals 0 as a null line, which is a trajectory of the velocity of the light, trajectory of the light. Okay, V is obviously affine parameter. Okay, so I take V as a similar affine parameter for the bulk trajectory. So bulk goes all the way. Imagine that this is G equals 0 and this is G equals 0. So bulk goes G non-zero and then come back to here. So I take again V as a affine parameter also for the bulk. Okay, good. So I choose V as a affine parameter, and then to go from south pole to north pole, V has an upper bound. Okay, and this came from simply because I take the phi equals 0 trajectory, and theta goes from 0 to pi, and that's why. Is it good? Yeah, I hope so. Okay, so that's the situation. So I start with the south pole. We want to reach to the north pole, V as my affine parameter, and then I ask. I consider all allowed bulk causal curve starting with two boundary points, G equals 0 in the south pole, and then we reach to the north pole, which is G equals 0, okay, through the bulk. Whatever trajectory has its causally allowed, I need to consider. Then my question is that for any bulk trajectory, I require the end point where V equals square root 2 pi, that corresponds to the north pole line, which corresponds to this line, okay? That's square root 2 pi. I allow only this region. I do not allow this region, okay? That's my bulk no shortcut result, no shortcut requirement, okay? All the trajectory which once go into the bulk, you are always to get time delayed. You never reach time advance through the bulk. That is equivalent to my bulk no shortcut principle. Okay, so that's the same as I am allowed to go through the bulk only in here. I'm not allowed to reach here, because if I allow to have reach here through the bulk, I do have the bulk shortcut. Okay, since I require there's no bulk shortcut, I require that it always reach only in here as hard as you go pass by the bulk. Only the boundary reach here. Once you go to the bulk, you are only allowed to here, because otherwise you have the bulk shortcut. Okay, so that is this requirement. Okay, this inequality is my requirement. You have only time delay through the bulk, no time advance through the bulk. Okay, so what does this mean? Okay. So I give the main punchline of my talk in just as intuitive as possible. So the result is the following. If the bulk metric is bad, okay, what do I mean by bad? I will explain later. If I have a bad bulk metric, I do have the bulk shortcut, obviously, okay? But if I have a good bulk metric, I do not have the bulk shortcut, right? So I want to classify what do I mean by good or bad. If I have a bad bulk metric, okay, which allows a bulk shortcut. So I want to give the constraint to the bulk metric, which should behave as good, so that it doesn't have the bulk shortcut. Okay, but note that bulk metric is, which I will gonna assume furthermore in later, but bulk metric is uniquely determined by the Einstein equation. Okay. Once we determine what is the initial condition for the bulk metric, the Einstein equation uniquely determines what should be in the bulk, right? Einstein equation is a secondary differential equation. Once you give the two initial conditions, the bulk solution is completely determined, okay? So my requirement that bulk should be good in such a way that it doesn't allow the no shortcut is reflected as imposing some condition on my initial condition, okay? Because initial condition determines the bulk metric completely through the Einstein equation. So my requirement for the goodness of the bulk metric is reflected as good boundary condition for the bulk metric, okay? But note that I already determine what is the boundary metric. In other words, I already determine what is the non-normalizable mode of the boundary metric, okay? So I have only freedom to tune the normalizable mode, right? because I already know what is a boundary metric. That is the same as determining non-normalizable mode. Okay. Once you specify normalizable mode, the bulk equation motion uniquely determine what should be the bulk metric. As a result, whether bulk metric is good one to not allow the bulk shortcut is uniquely determined. Okay. So my requirement for the goodness, in the sense that it doesn't allow the bulk shortcut, is reflected as imposing some condition on the normalizable mode of the bulk metric. Okay, hope it's clear. If I impose some condition of the normalizable mode for the metric, since normalized mode of the metric is the same as stress tensor on the boundary field theory, that is reflected as imposing some energy condition for the boundary field theory. The result is that it's very similar to the ANEC, but in curved space, instead of the ANEC, I obtain KNEC. That's a punchline of my talk. Okay.
Sorry, can I interrupt the second?
Yes.
But I think still it's a non-trivial statement that apparently like choosing different non-normalizable mode does not impose any condition. I mean, allows you always to satisfy this condition, right? So you said that like you're going to determine like, I mean, the condition on the normalizable mode.
Right. To be good for the bulk metric, yes.
Right, but I'm saying that like, I mean, also the fact that you have no condition, no restriction on the non-normalizable mode is also some kind of miracle, right?
Right.
Like,
so you're right. In the beginning, we expect that if we start with an extremely weird boundary metric, that is the same as starting with an extremely weird non-normalizable mode. Whatever we impose for the normalized mode, we may find some bad bulk metric which allows the bulk shortcut. That's what we expected in the beginning. Is that what you mean? Is that right?
That's right, yes.
Yeah, but what we found is that so far as whatever we do for the starting boundary metric, which is that whatever we do for the non-normalized mode, as we impose nice condition for the normalized mode, which is reflected as a good bulk metric through the Einstein equation, we do have the good bulk metric, which does not allow the bulk shortcut. That's our conclusion. So it's a bit non-trivial. I completely agree. And I do not have an intuitive understanding why we have such a freedom for non-normalized mode. But your understanding, your intuition, I completely agree.
So also there is no general proof of that statement, right? I mean that
as we study, we don't have to impose anything for the non-normalized mode. That's our conclusion so far.
Okay,
but
thank
we
you.
don't touch with everything, right? Any other question? So I hope my intuitive explanation is clear. So I'm just repeating what I say just in 1 minute. So good boundary theory, okay? Good boundary theory allows a good bulk dual, okay? Good bulk metric does not allow the bulk shortcut, okay? So what is a good bulk metric? Good bulk metric is determined by non-normalized mode, which is a boundary metric, and good normalizable mode. Because once we know normalized mode and non-normalized mode, Einstein equation determines the bulk metric completely, okay? So imposing the good bulk metric is reflected as imposing the good condition for the normalizable mode, okay? But since the bulk metric is the same as boundary stress tensor in the holographic dictionary, okay? This is the same as requirement some good condition for the stress tensor. The result is that it's very similar to the ANEC because it's obvious because we're imposing some condition for the stress tensor, which is a normalized mode for the metric. But it's similar to the ANEC, but it's slightly modified one. That's we coined as a KNEC. And that's a punchline of my talk. So I hope this is clear for everybody. Okay, hope this is okay. Then in the rest of my talk, in roughly half an hour, I just illustrate how we obtain this in the simplest example. Okay, that's a plan. So are there any question? Otherwise, I just go ahead. So I just give the concrete example, the simplest example to illustrate how we reach this conclusion. I just give the simplest example, but in our paper, we consider more generic situation. But in this talk, I just illustrate only the simplest example. So the simplest example I already mentioned is a situation where you have the boundary sphere and time. 2 plus 1 dimensional boundary.
Can I ask a question?
Yes, please.
So, well, as you explained, this normalizable mode is dual to the boundary stress energy tensor.
Yeah.
And can you explain how this boundary stress tensor is arising? Well, I mean, not in the language of ADS-Shefty correspondence, but are you exciting something? I mean,
right. So, okay, if we consider just pure ADS correspond to the boundary, then it's a ground state, right? But obviously, you want to consider any excitation in the bulk, okay?
Excitation by matter field.
Yeah, by
Is that
matter
what you mean? Bulk matter field? Or certain operators?
Excitation in the boundary language correspond to some excited states, literally. I mean, you have the ground state correspond to the pure ADS, and in the boundary quantum physics, you have the excited state. Is that right? Example is a black hole. Black hole is an excited state in the bulk, correspond to the thermal excited state in the boundary cell. Obviously, metric is deformed from the pure ADS. If you look at the normalized mode of the metric, that corresponds to the energy of the black hole or excited state. Is this clear?
Okay.
Okay.
So, Nori, just to comment on that, so as far as I remember, you consider only pure gravity here, right?
Yes, that's I'm gonna explain in next. Yes.
Right. Okay. Thanks.
Okay, good. So let me explain the simplest example more concretely instead of the blah blah blah. So let's just require this. I just require no bulk shortcut. The fastest way to reach from one boundary point to the other boundary point is through the boundary. Okay, or at most tie through the bulk. Bulk is usually at most tie or slower. Okay, that's the same as in this simplest example. U is greater or equal to 0. Okay, if this is a situation, we have the bulk shortcut. I don't allow that. So let's consider the bulk metric by this Pfaffian-Graham representation. That's probably all we know very well. That we do this Z expansion. Z0 is a boundary, and the bulk metric is determined step by step in the Z expansion. Okay, so n equals 0 correspond to the boundary metric, and that correspond to the non-normalizable mode. Okay, and subleading one is determined by the Einstein gravity. Good. So as Yanis already pointed out, I furthermore assume the following. The bulk space-time satisfies the Einstein equation, okay, as I mentioned in the beginning. But in addition, near the ADS boundary, I assume that the effect of the matter disappear quickly, okay? So this may replace as a condition that the bulk matter field is localized in the center of the bulk and decay rapidly enough near the boundary. And that is my assumption, okay? In the later, I just discussed how we can relax this condition, but in the simplest example, this is the assumption, okay? Good. So because of my assumption, near the boundary, stress tensor is determined, stress tensor is 0. So we have unique Einstein equation. So as I mentioned, once we specify non-normalizable and normalizable mode, how the bulk metric behave is completely determined by the Einstein equation. Okay, you have no freedom near the boundary at least. Okay, as we do this G expansion. So this is what I already mentioned here. Given the boundary metric, which is n equals 0, that's G to the 0th power, all the subleading coefficients are determined from the boundary metric completely. But let me carefully mention this fact in the following way. So n equals 0, that's a boundary metric. Okay. Once we specify the non-normalizable mode, n equals 0, the subleading correction n up to d, n less than d, are uniquely determined by this boundary metric. Okay, but once you reach n equal d, okay, this term is influenced by the normalizable mode. Therefore, once you specify also normalizable mode, the rest of the term all the way up to infinity, as we do the G expansion, as stress tensor effect disappear, Einstein equation uniquely determine completely the metric. Okay. So in order to avoid extra confusion allowed by the freedom of the matter field, I just assume that near the boundary stress tensor effect disappear. Okay, So you see why I assume this. Good. So explicit formula for n less than d are completely determined. Okay, that's determined by this paper, and I just write down what they wrote down in our notation. Since we use d equals 3, boundary field theory is 2 plus 1 dimensional example, I don't need this example. I just need only this. Okay. Since our example d equals 3, okay, d is 3. Okay. So n equals 1, 2 is uniquely determined. But n equals 3, since our boundary theory is 2 plus 1 dimension, n equals 3 is influenced by the normalizable mode. Okay. So once we specify boundary metric, which is non-normalized mode, in this g to the nth power expansion, n equals 0, that's boundary metric. N equals 1 and 2 is uniquely determined. In fact, n equals 1 disappear, and n equals 2 is this one. N equals 3 is influenced by the normalized mode, and so is the rest of the mode. Okay. Then once we specify also normalized mode, the metric, bulk metric is uniquely determined. I want to impose some condition for the bulk metric in such a way that it doesn't allow the shortcut through the bulk. That is reflected as imposing some condition of the bulk metric. Obviously, bulk metric is determined by the non-normalized mode and normalized mode. That is the same as requiring some condition for the normalized mode. Since normalized mode is the same as stress tensor with the boundary field theory, what I am requiring for the normalized mode can be interpreted as the boundary field theory. The result is some energy condition for the boundary field theory, and that's a punchline. Okay, hope this is clear. Okay, then the rest is just straightforward. Okay, so n equal d is a normalized mode. In simplest example, it's just simply normalized mode. Okay, which depend on the bulk state, what kind of excitation you have, both on the bulk and the boundary state, correspond to the boundary stress tensor wave of the ADCFT dictionary. Okay, which everybody probably know it. So that's a result. Okay, so we do the Pfaffian-Graham expansion, and stress tensor is related to the d equals 3, n equals 3 mode through this formula. Okay. So in our boundary 2 sphere, boundary is 2 plus 1 example, this n equals 3 in the g to the nth power expansion is a normalized mode, which is dual to the boundary stress tensor wave. Okay, normalized mode corresponds to some excitation measurement. Okay, that corresponds to measurement of the energy of the boundary cell. Okay. Okay, so precisely speaking, so far what I have said is very simple, and it works for as simple as this for odd dimension. If we consider even dimensional boundary field theory, there's an additional complication comes due to the anomaly. But we analyze this in the second paper, but it's complicated, so I just skip explanation of the even dimension in this talk. So now we are ready to calculate the bulk causal curve. So I consider the following bulk causal curve. Remember, our boundary is a sphere. Okay, so we have time, theta, and phi, but phi is irrelevant. I just neglect. So I just start with the theta from south pole to north pole. Okay, and just t and theta, I replace u and v. Remember that? Okay. So my boundary coordinate is a u, v, and irrelevant phi, but since I don't consider phi direction at all, I just phi direction to be 0. Lambda is my affine parameter. Okay. Now the non-trivial point is that we have to go through the bulk. Okay. So z, the bulk direction, also change as a function of the affine parameter. So this Ka is the bulk curve's direction. Okay. How the bulk curve trajectory goes. K is a vector of the direction of the bulk curve. Okay. So G is a function of the lambda. Okay. Lambda is affine parameter. But as I mentioned, I take V as my affine parameter. Remember that I have this and this and this and this. This V is my affine parameter. Okay. So I take V and lambda equal, so that's 1. I don't consider any direction along the phi because it's irrelevant, so that's 0. Okay. Sorry for that. This is my air conditioner speaking. Okay. So how z, the bulk direction, change as a function of the lambda, which is v, as a affine parameter. Okay, that's unknown. How u, okay, this is the u direction. Whether we reach here or reach here, it's a function of the lambda. Okay, how it's behave through the bulk is unknown. Okay, these are the unknown. Okay, and this is a bulk curve which I consider. Okay, hope it's clear. Phi is irrelevant, so I said 0, and v is the same as affine parameter, so I said 1. And how u and z behave as a function of the affine parameter, that's a question. Okay. I do this FG expansion, so z, the bulk direction, I do also in the g expansion, which I do related as epsilon expansion. Okay. Now you can think about how you should behave as a function of the epsilon and so on, so on. You just massage a bit and how causally it's allowed and so on. After a few minutes of the calculation, you notice the first expansion is epsilon square and so on, but that's technical. It doesn't have to bother about that. It's not important at all. Only the boundary condition I impose is that you start with a boundary point A and the south pole, and you should come back through the bulk to the north pole. So starting point is a south pole with a g equals 0, and end point is a g equals 0 with the north pole. So south pole, g equals 0, okay, north pole, g is 0, that's a boundary condition. But in between, g go to the positive, you go to the bulk. Okay. The bulk metric is here. It's a function of the normalized mode and non-normalized mode, and the boundary metric is this one. That's simple. That's a sphere times time. Okay. Good. So what kind of the bulk curve I am allowed to have? Well, just bulk causality implies that the curve should be time-like. That's it. Okay. I consider all the bulk causal curve as has its time-like. Okay. So this inequality, bulk causal curve, which is a function of this z and u, that's a non-trivial, okay, must obey this inequality, and that's it. As has it obey this bulk causality, I consider all z and u as a function of the affine parameter. Okay, so this inequality gives some inequality of this unknown function u, okay, and that's this inequality. So this inequality is a result of this inequality. Okay. So how do you obtain this one? You have to do a bit calculation, but it's not that difficult. You can work it out. Okay. So this bulk causality time-like impose this one. Good. So we obtain some inequality for this quantity. But what we want to acquire in the end is that this u as the end of the north pole, okay, should be bigger than 0. Okay. That is the same as this quantity's integration from south pole to north pole should be bigger than 0. That's the same as no bulk shortcut requirement. Okay, but this function, as it follows the bulk causality, we know some inequality. Okay, so now you see what I want to do. We impose this inequality into here, and then whether the resultant one can satisfy this or not, if we require some condition for the normalized mode. Okay, that's the same. So let's do it. So this is the inequality we want to impose from the no bulk shortcut. So we do this. Okay, so here we just rewrite this as a here. Okay, but here I have another inequality like this that came from the bulk causal curve. Bulk causal curve, the bulk trajectory should follow the bulk causal curve. This inequality reflects as this inequality of the this and this integrand relation. Okay. In the end, you obtain this inequality, but whatever you have for the bulk causal curve, this quantity must be bigger than 0, and that is our requirement, no bulk shortcut. Okay. So if we impose whatever you are allowed to have this one, impose this inequality, what kind of the condition you impose for the normalized mode? Okay, that's a question. Good. So let's analyze this one. Okay, this is the explain extension. So as you can see, you first worry about the epsilon square term. That's the biggest one. not that difficult to show that actually this quantity integration, that its minimum value is 0, as has this G1 follow its equation motion. So imagine this is the action, and you want to minimize it by the saddle point. Equation motion is this, and in this case, you can show this is 0. Okay? We want to make G's quantity as negative as possible, okay, and see whether it's violate this inequality or not. This quantity, what I said that this quantity can be 0 or bigger, always positive. Okay, so we said this is 0 because if this is positive, this is guaranteed. So we said this is 0 by taking G1. The G1 is a trajectory of the bulk in this way, in this epsilon expansion. Good. So if we require G1 follow this equation, this takes the minimum. The epsilon square term takes the minimum, that's 0. And in this case, you can also furthermore show that in such a choice, this becomes 0. So what we are left is that because this is 0 and this is 0, we are left with only this term. Okay? So I just eliminate it. G1 take this curve. So what we obtain in the end is here. Okay? So we require this. Okay? That's a no bulk shortcut. And this is a requirement of the bulk curve for the time-like direction. Okay? So we ask, when this condition is satisfied? That's the same as this one. This is the same as this one. You can see that it's a G3, that's a Gn, G to the n equals 3 in boundary dimension is D. Okay, so that's normalized mode. Now you know that this normalized mode is related to the stress tensor of the boundary theory. So obviously you obtain some condition for the stress tensor from the requirement of the no bulk shortcut. Okay. So it's very similar to the ANEC, but there's a slight difference. So this is proportional to the stress tensor. So let me rewrite this as a stress tensor. Shoot. This as a stress tensor because it's proportional. Okay. L, what is L? L is a boundary null direction. Okay, boundary null direction like this. That's L. Okay. But if it's ANEC, we don't have this factor. 1/2 is constant, that's okay. You can go outside of the integration, but you have additional weight factor G1. G1 obey this, where dot is a derivative with respect to affine parameter lambda. Okay. So we obtain very similar to the ANEC. Notice that if we, sorry for that, if we do not have this factor, it is ANEC. Okay. But because we have this additional factor, okay, G1, which is a function with affine parameter, we are having a modified energy condition. Okay. So in summary, what do we obtain? We obtain this as a stress tensor, and G1 follow this equation motion came from this saddle point, and D equals 3 is related to the stress tensor. Wrapping up all, okay, we obtain this equation. That's our conclusion. So let me explain. Here, lambda minus and lambda plus is a south pole and north pole in the simplest example, or more generically, it's a focal point, okay? It's a conjugate point of the boundary theory. Focal point is that if we consider the null line, okay, starting with the south pole, it goes up, okay, and converge into the north pole. And that's a focal point. And that's lambda plus and lambda minus. In our example, lambda equals 0 and lambda equals square root 2 pi, I suspect. Okay. Additional factor, this one, where eta is a Jacobi field. What is a Jacobi field? Jacobi field is, for example, in the sphere case, you start with the south pole and you send the two signal of the light. It goes up in the equator, the distance of the two light become maximum and then converge to 0 again. The distance between adjoining next to each other's light, this distance is Jacobi field. So it's a function of the lambda, affine parameter. So you start with the south pole at v equals 0, and then at v equals v0, square root 2 pi, you reach to the 0. But in the equator, it's reach maximum and it's 0 maximum and 0 again. In our previous example, Jacobi field behave as sine function. 0, maximum, and 0. So the non-trivial point is that if you require that no bulk shortcut, what we obtain in gen for the condition of the normalized mode gives a, instead of the ANEC, average null energy condition, but you obtain this weighted energy condition where weight is determined by the Jacobi field of the boundary topology, boundary geometry. Okay.
So
if you have yes.
So the Jacobi field is just depending on the geometry of the boundary.
Exactly. So in the case
of conformally flat manifold, is this equivalent to the usual ANEC condition?
Exactly.
So you're generalizing it to non-conformally flat.
Yeah, generalizing it to the curved space, I would say.
Okay. Thank you.
Okay, so the extension to the flat space I just mentioned quickly in a few slides later, but let me just explain the terms. So Jacobi field is determined in terms of the boundary geometry. Okay, L mu is a boundary null line. Okay, and this is a focal point. So that's the obtained result simply following the requirement that there is no bulk shortcut. Okay, so in the simplest example, we show this example, but in more result we summarize in the paper where we consider more curved boundary theory and so on, we analyze it. Okay, but anyway, this is our punchline. Good. So as Sok already pointed out, the extension to the flat space limit is straightforward. So as I mentioned, lambda plus minus is a conjugate or focal point. Okay, now if you take the flat space limit, the sphere become infinite radius. So the focal point become obviously minus infinity and plus infinity. Okay, and in flat space limit, local curvature becomes 0. The Jacobi field, the distance, the Jacobi field is non-trivial because of the curvature. Obviously, it follows the Ray-Chadwick equation. Okay, but if it's a flat, it's a straight.
Excuse me, but I think I asked a slightly more general thing. The conformally flat boundary. Like the sphere example that you did is if you add the time direction as 2 times r is conformally flat. So starting from the ANEC in flat space, I was asking whether you can derive your Jacobi field KNEC condition from the usual ANEC.
Okay. Maybe I may not be answering directly your question, but the following can be done. Starting with a flat space, by the conformally map, you can make it the space into sphere times time, right? That's a trivial.
Exactly.
And then you obtain this result. And that is a result which not by us, actually this guy did after our work.
Okay.
So this exact result you can do by the conformal map starting with the ANEC of the flat space. By doing the conformal map, you do actually have this weight factor.
Okay, thank you very much.
And that's what this guy did after our work. We didn't notice this point, but it's totally consistent. So okay, so anyway, so that's what I want to say. It's consistent with the flat space ANEC just by conformal map. But in more curved space-time, we can derive this one. But what I want to emphasize in here is that instead of the ANEC, if you follow naively the no bulk shortcut principle, you do need this weight factor. And additionally, the good point of that this weight factor is totally consistent with the following point that, so let's eliminate all of this. This formula is actually conformally invariant. That you can show it. So in D equal odd dimension case, you can show that this formula behave nicely by the conformal transformation, and it's consistent. In D equal even case, there's a more complication came from the anomaly, but at least in D equal odd case, we show that this transform nicely under the conformal transformation. Okay. So what we want to say is that instead of the ANEC, where it is KNEC. Okay. What does K mean? Conformally invariant, at least in the D equal odd dimension case. But what I want to say is that this weight factor is involved. That's all I want to say. Okay. So there's a few comments before I reach to the discussion conclusion. So actually our result reduced to the flat space limit. And I should mention for fairness, this Kelly and Ward, they did first for this ANEC no bulk shortcut principle from the AD shifty okay, in the flat space limit. So fairly speaking, what we did is that there resulted generalization into the more curved boundary theory. Okay, that's fair way to say what we have done. Okay, so you have our derivation is a curved space generalization. The Kelly wall they did in the flat boundary. Okay, so I already mentioned many of these. Our formula, at least in D equal odd dimension, is conformally invariant, and weight factor is crucial. Without that, it's not conformally invariant. Okay? And this gentleman, as Sok already pointed out, derives the same result of this weighted factor by the conformal map from flat space to sphere times. Okay, good. So weight factor is crucial. That's the main message. So my time is up. I just give a quick final discussion and open question in just 5 minutes, and then I stop. Is that okay? Okay, good. So, okay. So in even dimension, okay. So in odd dimension, just this formula in 3 dimension, 3 or 5, and this formula works. That's what we showed in the first paper. But more complication arise in D equal even, okay, due to anomaly, okay. But in D equal to, it's simple because D equal to space is only one line. There's no curvature notion, so this weight factor disappear. Okay, we need a curvature, local curvature, to have the non-trivial Jacobi field. So in D equal to, it's simple, okay, as odd dimension. But for example, D equal 4, it's become complicated. What we obtain after analysis? That suppose we consider 4-dimensional boundary metric is like this. Okay. So what is this? Before we don't have this. Okay, UV and just phi. Now because we have additional direction, the boundary 4-dimension have additional direction. Okay. Given this a bit arbitrary F and R as a boundary metric, we do the similar condition, similar analysis of the no bulk shortcut. Okay, what does that mean for the normalizable mode of the bulk metric? Okay, which can be interpreted as a boundary field theory stress tensor energy condition. Our result is the following. Okay, looks complicated, but what I want to say is that this all quantity in the right-hand side is uniquely determined once you specify the boundary metric. Okay, some complicated quantity. In the simplest example, like sphere, okay, S3, many of the terms disappear. But if you consider more squashed or complicated geometry, the right-hand side become a bit non-trivial. Looks complicated, okay? So just to illustrate, we just give the example. Suppose boundary is a 4-dimension with the bulk is a 5D Schwarzschild black hole. What this result imply? We just plug in, we just calculate the right-hand side, many of the terms disappear, and so on. What we obtain in the end is that the energy condition, this inequality, simply become this inequality, and that's as simple as we expect. And bigger.
Can I have one check?
Yes.
The D equal 2 case, why you say we have the same condition?
For D equal 2, we have only one space and time. So
I'm concerning about the CFT on a cylinder where basically we have ANEC violation, whatever integral there. TVV is negative.
Well, TVV integration is what we require for the ANEC.
Yeah. But the TVV itself is negative and constant on a cylinder because of this Casimir energy and corresponding pressure component.
Good.
And so I'm a little bit confused about your statement.
Good. So no, you notice already, I already assumed a couple of things. I assume that the usual holography, that's probably okay. But the near the boundary, the effect of the stress tensor disappear and so on. Right, that's I assumed. Because if we have freedom for the stress tensor near the boundary, dependent on what kind of the matter field you choose as a stress tensor, the freedom added up to determination of the bulk metric. So that may give some extra confusing point, which I avoid in this talk. So I do not have the sharp answer to your question, but possibly
Well, in
restriction-
CFT on a cylinder, basically, well, everything is determined by the central charge.
right.
And so this is a rather general result for the ground state.
I agree.
This is for the ground state.
Let's see. Right, D equal to be honest, I have other extra confusion. So let's see. Right. So how this is consistent with the main example in terms of
for two case, for instance, we don't have this is basically a circle, and so we don't have a conjugate point.
Right. We do not have the literally conjugate point, but we can consider if it's a circle, we can consider the say theta equal 0 to theta equal pi as sort of the similar conjugate point. We can think in that way.
Yeah, in that case, well, it seems to me.
So
we have an ANEC example of ANEC violation.
Right. So I can phrase your question. I do not have the sharp answer to convince you now. I agree with your statement. How do we interpret how it's consistent with my result? We have to work a bit more. So my honest answer directly is that I do not have the sharp answer. Yeah,
okay.
But in the case of Schwarzschild black hole that you just have on your side,
this 5D1.
Yeah, even for that you don't include vacuum energy, right? You know the
vacuum energy
next to last line demanding mass being positive or some.
Right.
So the second term on the left hand side is the vacuum energy.
Second this one.
Yeah.
This quantity.
Yeah.
That came from this all complicated unknown quantity calculation. Okay, I don't have the intuitive understanding of how this can be understood intuitively, to be honest. But just requiring no shortcut through the bulk, literally reflect as what kind of the condition for the normalized mode, just calculation, we obtain this result. Now you ask what kind of the interpretation as a
basically doing geodesic calculations and so on, right?
It's a geodesic calculation, exactly.
And how can that see the vacuum Casimir energy, which is highly quantum and so on? Is it possible? Well, I think that's Dongsu's question. I mean,
right? Yeah, I agree. Casimir energy is a quantum effect in the boundary field theory. I completely agree with that. But that energy must be sort of reflected as some geometrical condition from the bulk viewpoint classically. That's what we did expect it. Maybe I'm wrong, but that's what we expect.
So can I comment on that? So indeed, I mean the Casimir energy on the field theory side is encoded precisely like on these anomaly terms in the bulk. So whenever you have even dimensional boundary, there is actually a Casimir energy that you can compute holographically, but it comes from these logarithmic contributions. So, and it has been computed actually, like, for example, for 5-dimensional black holes. So I believe, I think Nori told me that, they haven't checked that, but I believe that this should be related indeed to the Casimir energy that you can compute holographically from the bulk.
Right. So through the anomaly, this vacuum energy is reflected as some anomalous time.
But tell me if I'm wrong, but maybe my impression is that when you were first at the earlier part of your talk, when you're stating the no bulk shortcut conjecture, I think you're comparing the geodesics on the geodesics on bulk and boundary, and that led to your conjecture, right? So it seems that you're using semi-classical pro-particle calculation both in the bulk and boundary. So I don't think
that's right.
I don't see anywhere where this quantum effect can enter in, even at the boundary.
Well, right? That's true for the odd dimension. That's true for the odd dimension. But as Yannis pointed out, I think in the even dimension through the anomaly, the vacuum energy is reflected through the anomalous term. Isn't that right? That's what I thought. Maybe I'm wrong.
That's right. The vacuum energy
is asking how this simple classical geodesic argument reflected quantum effect. That's what you're asking.
Yeah. You mean your earlier argument seems super simple, having to do with semi-classical point particle geodesics, right?
Right. I completely agree. Yeah, let me think. I don't have the sharp answer at this moment.
Okay, thank you.
So my time is up. Let me just wrap up. So the open question discussion. So the simplest open question is that what this anomaly term, which involves this complicated term, will imply intuitively. Okay, I do not have the understanding. And the one interesting thing is that the right-hand side can be negative if we consider weird boundary metric, which involves a non-normalized mode. But as you already know, this may not be so surprising since in compact space, the Kashmir energy can contribute to negativity, as you pointed out already through the discussion. Okay. So a bit weird thing is that we consider the compact space or positively curved space and also flat space limit. We can also do the same thing for the hyperbolic boundary, which is a negatively curved spacetime, okay, which doesn't have any focal point at all. You do the same analysis. You require no bulk shortcut. And what does this imply for the normalized mode for the stress tensor? Okay. It turns out, as we study, no bulk shortcut principle does not yield any non-trivial condition for the stress tensor. Okay. Bulk no shortcut is automatically satisfied, as we studied. However, this is puzzling because we do expect similar energy condition must be satisfied even if we consider the quantum field theory on the hyperbolic boundary. Okay, so how is it consistent with what we have done, ADCFT? And that's an open question. We do not have the understanding at this moment.
Can I ask a related question on that? If the time is okay.
Well,
I mean, suppose that you put a conformal field theory on a negative curvature manifold, then the conformal mass square term is negative, right? So wouldn't there be any tachyonic direction? So you won't have any lower bound on energy conditions or whatever, it seems to me. Is that related to what you're saying?
I think so. I think it's related. But I don't have the sharp answer at this moment.
Okay.
Right. So as an open question, we assume that the bulk matter field decays sufficiently rapidly near the boundary. Now we can relax this assumption, of course. For example, the effect of the gauge fields near the boundary does not decay enough, so its back reaction is crucial. Okay. Or suppose we consider, say, holographic superconductor, such effect we have to take into account. That's reflected as a good bulk metric and also good boundary gauge field, and that's reflected as a condition for the not only stress tensor but also boundary current. So it's interesting to investigate furthermore along this to see what kind of condition we have to additionally impose for the currents and so on. Okay. Now, finally, we discuss whether bad or good. Okay. In fact, Gao and Wald, well, it's not 1900, okay. Gao and Wald proved that if bulk matter field, so this is a different story. Gao and Wald long time ago proved that if bulk matter field obeys the bulk ANEC, this is bulk ANEC, then no bulk shortcut principle is satisfied, that they have shown in long time ago. Now, the final question is, can we read the behavior of the normalized model in these good bulk metric, where bulk obeys a bulk ANEC, therefore no bulk shortcut is allowed? In such a situation, can we read off the normalized model behavior and reinterpret in terms of boundary field theory, and that should give the more generic condition of the boundary field theory? Okay. We studied this project since because we want to investigate what kind of the non-trivial condition we have to impose. Otherwise, we get inconsistency. One of the inconsistency is that we do have the bulk shortcut, okay, to investigate which kind of the boundary metric is allowed for the ADCFT. And the final goal is that we want to read off the more generic condition. Okay, so for that direction, we do the first step. You can say in that way. So that's it. Thank you very much.
Okay, let's thank Dori for great talk.
Thank you.
So let's start discussion.
So Nori, do you have a covariant version of this Jacobi field integration?
Covariant value, in what sense covariance?
So suppose you take like an arbitrary boundary metric, right? I mean, like you don't specify that it's a sphere or something. So is there a way of writing this covariantly? Like, I mean, for example, something like, I mean, it should be proportional to the determinant, to the volume element, right? I mean, in some sense. So because that would make the stress tensor covariant, volume variant.
Wait, could you repeat again? I don't understand your last statement.
So, I mean, you want something, right? I mean, you said that this condition, like this KNEC, right? I mean, it's conformally invariant.
Right, with weight factor, right, yes.
Right. So since the stress tensor, right, I mean, is a marginal operator, right? I mean, so you would want something that is multiplied, I mean, that has, like, roughly speaking, is the volume element, right? I mean, of the boundary metric. To make that, like, conformally invariant.
Okay. It's a local function with how the metric will be. Well, if you say volume, let's see.
So the question is like whether
local information was a curvature completely, maybe. Okay.
So the question was like the original question was if you have like an expression in terms of this boundary metric, like I mean, without specifying the metric explicitly.
Your question is that can we write it down without specifying the boundary metric?
Yes.
Well, of course, we couldn't consider all of the possible metrics, but we consider quite generic one, given some unknown function with a boundary metric. Okay, we do consider the situation where, in average, it's a positive curvature. Otherwise, we do not have the focal point. But locally, it can be fluctuating, and it does have the focal point. In such a many generic situation where we have unknown generic function for the metric function, we do derive the similar result where it's written in terms of Jacobi field, where it obeys the local boundary metrics Jacobi field equation. That's our conclusion.
Right.
So not generic, but quite generic in the sense that introducing some unknown function, arbitrary function, but we do still derive the similar result. In that sense, right. It's quite generic. But in terms of the volume form covariance, I never thought about that, so I have to think about that.
Okay, thank you.
I think people already asked many questions.
Right. Is there any other questions? So I think there were so many questions during the talk, so probably no more question. Okay, it seems that there is no more. So let's thank Nori again for his nice talk.
Thank you. Thank you very much.
Thank you very much for Nori. So yeah, this is the end of today's program. Yeah, so we will meet tomorrow morning at 9. Thank you very much for everybody.
Bye-bye.
Okay, guys. Good night, I guess. Good evening.
Good night.
I'll see you guys tomorrow. Thank you, Nori, again.
Yeah, bye-bye.
Thank you, bye.
Thanks a lot.